So now over to our next talk. It's about accelerated global warming, current facts and near-term consequences. So what we all should know, what will happen to us in the next few months, years, not so far away. And I present you Volker Wittphal. Hello, Volker.
Hello to Vienna. Hello, Claudia.
Hello. Yes, you're on the other side of the world currently.
No, just on the other side of Europe.
Just on the other side of Europe. Okay, but it's
Yeah.
great. This is one of the really cool things about Privacy Week 2020, that we do have the possibility to connect to people all around the world, to have them here do their talks. I'm really happy that you're here, but I think you brought some not so great news to us, right?
Well, we will see. It depends how you define bad.
Bad or worse?
Well, no. Well, I thank you very much for the invitation to give this talk today. Because when we discussed before Privacy Week, if this could be a topic, in principle, it's system and it's relevant for everybody on Earth. So I guess the facts should be something that we should share with everybody. So let's start.
Yes, in a minute, everybody can also ask us questions.
Oh,
so
yeah.
Please go to privacyweek.at/ask, or you use the button on the streaming site Frage stellen, which is German for ask. And the other possibility is to write us on not Facebook, there we're not. We're on Twitter, actually, right? We're on Twitter and on Mastodon, and you can post us questions with the hashtag PW20 and PW20 online. And now, please start.
Yeah, thank you very much, Claudia. Well, how did I come to this topic? 1 year ago, I was asked that we, in the institute where I'm working, write something regarding sustainability and climate. And when I start to dig into the facts and into the physics, I found some, let's say, clues that I would like to share also with others who would like to understand how global warming is working. And what I have now composed for this presentation is just, let's say, summary of some facts, some physical facts in a very easy way to understand, as well as some current news from the scientific society. So if you look back, the 19th year since 2001 till 2019 have been the 90th of the 20th warmest years since we measure temperature and weather. So you see there a diagram where you have the deviation of the temperature due to the time between 880 and 1900. And you see that we are today at 1.1 degrees Celsius above this, let's say, reference value. So there is a so-called climate action tracker where you can see the warming in relation to the pre-industrial average, where we are today, where the Paris Agreement from 2015 is located, and also the, let's say, potential temperatures that we will achieve around 2100 by the current policies and also by the current activities. And you see that the thermometer has some different colored areas. These areas are areas due to the thresholds of the temperature that should appear with tipping points, but we come back to the tipping points later. So we all have now the news that it becomes warmer, but why? And to understand why the Earth is heating up, you have to get a little bit of physics, and I try to do it in a very simple way, not maybe always very correct, but I try to give you an understanding how the warming is working. So if you have the sun, you have an incoming solar radiation that is usually a shortwave radiation, visible light, ultraviolet light, infrared light. And this is, well, let's say, falling on a celestial body without an atmosphere, like an asteroid. So what happened then is that some of the sunlight is reflected, like 30% in average of a, let's say, asteroid. And everybody is also observing radiation. So because of the structure of the body, the temperature of this asteroid is minus 18 degrees Celsius or 255 Kelvin. And the radiation that he will give back to space is not in the visible range, but in the infrared range. So the asteroid is giving 70% back radiation, but just in another spectrum. If we look now to the Earth, and assuming that the atmosphere of the Earth is roughly just depending on nitrogen, oxygen, and argon gases, and we have also the incoming solar radiation that hits the atmosphere, we will have a similar situation that we have 30% reflection and 70% radiation in the infrared spectrum. Why? Because all these three gases have no interaction with the incoming sunlight. So if you look around, the surface temperature of the Earth is not minus 18 degrees Celsius. So the reason is very simple. If we look at the composition of the atmosphere, it's really 99.96% share of nitrogen, oxygen, and argon, but 0.04% of all the other gases. And these gases are the reason why we have a planet that is not an ice planet and also not a desert planet. And if you look very close, then you see on top there is carbon dioxide, CO2, that has 0.036%, means it's roughly 90% of the gases next to the three main gases is carbon dioxide. And you see there are other gases that are given not in percent, but in ppm, means part per million, or ppb, parts per billion. So these are very, very low shares in terms of volume shares. But these gases are the reasons that we are on a, let's say, planet where we have habitable conditions. So if we now go again back to a model that everybody knows, you probably know this greenhouse model of the Earth and the atmosphere for climate. And the greenhouse model is a very simple idea that you have between the surface of the Earth and at the top of the atmosphere, you have a special glass plate. In this case, you have a kind of glass ball, and between Earth and glass ball, you have the atmosphere. And in this model, usually the glass plane has H2O, water molecules, and also CO2 molecules. And what happened now if you have this special model, or this, actually it's a very simple model. The idea is that, like on an ordinary window, the visible light, the short wave radiation, goes through the window, and the heat, so the infrared radiation, stays on the side of the window. So it's like a wall for the infrared radiation. And if we now calculate this on a very simple model, of course, we have again the 30% reflection. But then, due to this glass plate, we need, because of thermal physics, also the 70% let's say radiation from the surface to the space. And because this has to be equal over the whole surface of this, let's say, glass ball, it's not only above but also below, means a back radiation back to Earth that has the same value of 70%. That means to radiate this 140%, we need a higher radiation from the Earth. And if you calculate this very simple model, then you end up by a surface temperature of 30 degrees Celsius, and the glass plate of the atmosphere has again this minus 18 degrees Celsius. And you see this is a very simple model that is not fitting well to our current situation of 80 degrees Celsius on the surface of the Earth. So this was just to show you how this simple model works, and to give you an idea about this radiation and what the molecules are doing. I'll show you now what happened in the spectra of the radiation. So if we look now at the incoming light of the sun spectrum you see in the top left, you see a dotted line. This is the Planck spectrum for a temperature of 5,700 Kelvin. And you see the let's say, the bolded line. That is the spectrum that the sun is emitting, and that is coming to the start of the atmosphere. And the yellow surface below the curve is the spectrum of the radiation that will reach the atmosphere. At the ground, you see that this spectrum has some losses. You see below UV standing for ultraviolet. This is completely gone because there is the O3, the ozone, that absorbs this very shortwave radiation. And that is also the reason why we stay healthy here and will not be killed by the radiation of the sun. You see also that the H2O bands have a very huge impact to the spectrum of the light that is coming from the sun. So there are some processes between the glass plane of the atmosphere and the surface that occurs that are not involved in this very simple model that I have shown you in the middle. If we go now to the thermal radiation, to the infrared radiation, then the surface of the Earth has these, let's say, spectrum that it's sending. And on the inner side of this glass bowl, there is a back radiation like these. And what you see there is a peak around 7 micrometer that is caused by also H2O. And you see another smaller peak of ozone next to this. And then there is another huge peak around 15 micrometer caused by carbon dioxide, and another one caused by H2O again. And if you now subtracted these both spectrum, then you get the actually spectrum that is going through a window, through an atmospheric window, and going outside the space. So that is what is ending up there. And to explain by a physical way what happened through the CO2 emission, the peak in the middle left spectrum will increase, and by this, the window that you have in the top right will become smaller and narrower. This is what happened by the CO2 concentration. This was just to show you how the real spectrum is working, and to show how complicated actually the processes in atmosphere are. I have another sketch from a scientific side. So you have, again, the shortwave radiation, like we have seen, the incoming solar radiation, and you see there is the observed spectrum by the atmosphere, what we have seen by the ozone layer. We have, again, also observed at the surface. We have reflected at the surface. We have reflections by the cloud also. and we have also radiation that goes again up into space. So infrared is even more complicated. You have convection there, you have transpiration there, you have the long wave radiation of the surface, and also next to this in the right down corner, the observed radiation by the surface, the back radiation, like I said. You see also the clouds are emitting infrared radiation. Even the atmosphere is emitting, and this atmospheric window, what I have shown you before, is here also, but you see it's just 40 watt per square meter, and you see the escaping long wave radiation into space there also. So this is quite complicated, and it's also not that easy to calculate. But this gives you an idea why it's not that easy to understand how climate works, and even to predict how climate will change, or what are influences and how huge are influences. And some influences, like also the H2O influence, is not completely understood till now. So if we now go back again to the border of, let's say, space and atmosphere, we have, of course, the incoming radiation, the shortwave and the infrared radiation. And in an equilibrium state, we would have also the outgoing radiation of the shortwave and the infrared. And in an equilibrium state, we would have a delta of 0. But the delta is not 0. And this delta is called radiative forcing. And radiative forcing means that you have energy in the atmosphere stored by the incoming radiation if you have a positive delta. If you have a negative delta, it means a cooling down of your atmosphere. And this radiative forcing is a measure also of the impact of different influences. And here you see an overview that is given by the IPCC, the Intergovernmental Panel for Climate Change. And what you see here are the values for radiative forcing by emissions and drivers. And you see CO2 has a very huge impact. That is the very large bar on top, the red one. You see also methane influence and other gases. And what you see also at the bottom of this diagram, that the IPCC has written down the radiative forcing relative to the value from 1750. And you see that from 1950 to 2011, it increases from nearly 0.5 up to 2.3 watt per square meter. And the current weight value today in 2020 is above 3.0. So that means more or less on the right end of the scale that is given in this overview. So this gives you the idea how it works. And to understand now the situation with the carbon dioxide, we just have a look into the past. So in the past, we have had different concentrations of carbon dioxide in the atmosphere. And to explore these values and to analyze it, researchers have taken a cone from the Arctic ice shield, and then they have sliced it into many slices, and the gas that was included in the ices, they have analyzed in terms what kind of gas and what concentration of gas was in the slide. And so they could give a very precise overview about the concentration of different gases in the atmosphere in the past. And this is the blue curve that you see in this diagram. And you see also the axis on the left side for the concentration in parts per million. So by this, you can see that there have been changes also in the past due to some natural effects. And what you can also see that the red curve, that is the corresponding temperature change here in relation to the present temperature for on an atmospheric level. But this presence is, you see, it's from 1999, so it's already 20 years ago. And you see both curves are quite well corresponding. And what you can see by this, that over a few 100,000, in this example 400,000 years, the concentration of carbon dioxide was always in a range from 180 in ice ages or during ice ages and around 280 in warm ages. So this is the past, and you see that this temperature change in average has been quite well adapted with this. So we have started to measure carbon dioxide in the 1950s. And when we started to measure, we started with 315 parts per million in 1958. Actually, I have to put this value on the other side, on the right side of the scale, but never mind. I want to show you where we are now. Because 10 years ago, we have already been at 390 parts per million. And this is just in scale with the other values that you see in the curve. The current value of 2019 is 410 parts per million. And that means that we are 130 parts per million over the concentration of carbon dioxide that we have had during warm times. So to put it in a very pragmatic way, if you want to go back to a, let's say, warm time status again, you have to reduce the carbon dioxide in the atmosphere by a third. So a third of the current carbon dioxide has to be removed, that we come to a equilibrium state of energy and temperature that we have had even in the Middle Ages or in the pre-industrial centuries. So if you see now also the dots that I have placed on the above the diagram, these are just values from 70 years, 60 to 70 years. And if you compare this with the time axis, this is less than a pixel in the slide. So what happened during the last 100 years is that we have increased the value of the carbon dioxide concentration by more than a third. And the radiative forcing gives you a clue that we still get the warming upwards, not downwards, because we have not the steady state where we have this equilibrium. So that's the fact that we are facing. That means we have to take carbon dioxide from the atmosphere to come back to a stable climate again. So if we look now at the atmosphere and the rest of the Earth, there are three huge storages for carbon dioxide or for carbon. In the science, they talk about the carbon cycle. And the three storages for carbon are the atmosphere, all the oceans, and the land. And by land, they mean the biosphere with all the plants, flowers, but also the ground, even with the, let's say, with the gases that are stored in the iced ground, in the permafrost. And there are exchange flows between these three storages. So you could say the exchange between the oceans and the atmosphere is not directly influenceable because this is so huge and there is no regulation that we can use. Between land and atmosphere, we can partly influence the exchange of CO2 due to, let's say, farming management and also to land management. We have some influence there. And if you look now at the flow, I found for 2 years, for 2006 and 2012, 12, some values in the science. The ocean, all the oceans in total is our greatest drain for carbon dioxide. Per year, the oceans are able to take 2 gigatons of carbon, and on the land it's different, and it's quite harder to define. In 2006 it was 1 gigaton, in 2012 2 gigatons, due to the effect that the, let's say, CO2 has also influenced the growth of some plants, but you have also a drying of plants, so the 2 is a question mark for today. So if you see this, you could say per year ocean and land are able to store between 3 and 4 gigatons of carbon. And we have another source for CO2 exchange. These are the fossils that we burn for our technology, for our warmings, for our society. And if you see now the volumes that we have had as emissions in 2006, it has been 6 gigatons. That means we have had 3 gigatons plus that we increased to the volume of the atmosphere. And in 2012, it have been even 9 gigatons that we have emitted into the atmosphere. So the delta there have been 5 gigatons that came additionally in 2012 into the atmosphere. And if you look at the current value in 2019, the emission has been around 10 gigatons carbon. So if you just think about becoming CO2 neutral, it would mean that we need, next to the existing drains, a drain in the dimension of 3 times all oceans of the globe to become CO2 neutral if we don't change our emission from today's volume. Even if we would cut it by 50%, we would still need roughly 1 additional ocean as a drain just to become CO2 neutral. These are the dimensions, what we are talking about. And remember the long time concentration of CO2 and also the influence and the impact we gain now by our emission. Then you get a first idea what we really could achieve regarding our ambitions and activities due to CO2 reduction. Let's have a short look to the CO2 emission. Where are they coming from and what is the amount? You have seen the carbon cycle was with the measures of gigatons of carbon. And here we have now megatons of CO2. At the end, you can compare these just by recalculation. Due to the fact that the carbon dioxide has two oxygen molecules, you have to divide the number of the megatons you have here for carbon dioxide by the number of 3.66, and then you get roughly the amount of carbon. So in general, it's the same measure, but you have to recalculate it. What you can see here now, these are numbers of British Petrol that gives every year a kind of statistical review of energy consumption. You see that the hugest amount of emission is coming from Asia. North America is very stable, Europe is very stable, and you can say also South and Central America as well as Africa are are very low emitting regions. And if you see now, just to complete it, what we emitted last year, we have been at 37,000 megatons of carbon dioxide, and in 2017 we have been below 35,000 megatons. So this is just the dimension of the emission that we have done as humans. But next to that, we have had last year and this year this bushfires in Australia that causes additional 830 megatons of CO2 emissions. And just for you as a comparison, the total global air traffic in 2018 has caused an emission of 980 megatons of CO2 emission. So it means if we would avoid to fly roughly 1 year, we could compensate this additional CO2 emission by the bushfire. But at the same time have been there similar large fires in the Amazon as well as in Russia. So the emission that we cause are still high and even higher as we usually have just in the small figures and facts. Just to give you an idea who is behind this huge emissions, by the shares of 2017, you can see that China is the hugest emitter of CO2 with 28%. India has additional 7%. Germany has 2.3%. On a global level, the total EU just 10.6%, and the US 15.2%. And if you now think about a reduction of the global CO2 emission by 50%, you probably have an idea who you have to take with you that you can achieve your goal in a few years. Well, I told you about the Intergovernmental Panel of Climate Change. These institution that has also caused the climate agreement in Paris in 2015. And in 2018, in October, they released another report that is called Global Warming of 1.5 degrees Celsius. And there they assume that between 2030 and 2052, the global warming will reach 1.5 degrees Celsius. This is the global mean surface temperature, of course. And what you see below is what it means. So in the left, you see the temperature distribution on the surface at 1.5 degrees Celsius. And in the middle, you see the mean temperature change at 2.0 degrees Celsius warming. The difference of both you see in the right. And you see that these warmings go up to 4 degrees Celsius in some regions compared with the average temperature today. And what this report says, to make it very ordinary, is 1.5 degrees Celsius is bad, 2.0 degrees Celsius is even worse. And because it's very abstract, I try to give you an hint what it means to have 2 degrees Celsius warming. If you have a 2 degrees Celsius warming, the scientists expect that the Mediterranean area dries out and the strip from the Middle East, starting in Syria up to Pakistan, will become uninhabitable for humans. You can see this if you look to the right diagram. There you see in Asia this orange glowing area in the north of India. This is the area where it becomes very hard to survive for humans when the temperature will rise up to 2 degrees Celsius compared with the pre-industrial century. So this is the difference between 1.5 degrees Celsius warming and 2.0 degrees Celsius warming. And there's an organization called World Meteorological Organization, and they announced this year in June that they expect a probability of 20% that till 2024 we will reach a temperature of 1.5 degrees Celsius in average in 1 year. So that means even the current prediction is faster, or let's say earlier than the 2 years ago done prediction by the IPCC, who expected the warming of 1.5 degrees Celsius for 2030 till 2052. So that means we have really a rapid warming. And in the beginning, I told you something about tipping points. And before I go to that, I just want to explain you a bit about the simulations that have been done by the IPCC. For the simulation, they have scenarios they call representative concentration pathways, where they assume a certain concentration of CO2 and temperatures that probably would be reached or not being reached. And you see on the right side of this diagram the likelihood to stay below a specific temperature. What you see for 450 ppm CO2, that we probably stay below 2 degrees Celsius. And this is the best case scenario of the 4 scenarios from the IPCC. You see there are 3 other scenarios, and the worst case scenario expect 1000 plus ppm for the RCP 8.5 scenario. And probably we even will go then above 4 degrees Celsius. So if you remember that the concentration is currently at 416 and that we are still emitting, probably we will also fail the RPC 4.5 and maybe also RPC 6.0. But in August this year, scientists published that due to the cumulated CO2 emissions from history, the future developments can only be predicted by the use of the scenario RCP 8.5, what is now red colored in the diagram below. On the graphic on the right side, left side, you see the prediction for the cumulated emissions since 2005. The red bar in 2020 represents all the cumulated historical emissions. And the dark blue one is the one of this scenario RCP 8.5. And then you see a black bar for 2030 and 2050, as well as a gray bar. And these are the predictions for the cumulated CO2 emissions for the next decade and the middle of the century. And you see that they only fitting to the model of the last one, the RPC 8.5. So if you conclude this, then we will expect that the warming will still go on, even if we stop immediately to emit any CO2 because of the equilibrium state. And we probably can't reverse it into a cooling of the Earth. I mentioned the global tipping points at the beginning, and tipping points are events that when you pass them, you can't stop the process behind. And the scientists expect for a threshold of 1.5, 2.0, and 3.0 temperature, global warming due to in relation to the pre-industrial age, the beginning of these processes. And it's not a dedicated threshold, it's around this. That means you have a few degree, maybe a few percent below or above, but around this age it will start. And What you see is we are now at 1.1 degrees Celsius, and what they expect there, you can read by your own. They expect that the Amazon rainforest will get a dieback when if it's not obtained by CO2 facilitation. You see that that they also expect a blanching and dying of coral reefs up to 2 degrees. The Greenland ice will start to melt, the West Arctic ice shelf will loss, and so on. So these are all things that start, and these events cause a cascade of other events that cause a feedback loop to the warming. So when we reach now 1.5 degrees Celsius, some of these feedback events start, and we have no idea how they interact with each other. This is from the mentioned study of the IPCC regarding the 1.5 degree warming. What you see here is they have these kind of, they call it 5 reasons of concern, RFCs. And these are going with temperatures, like you see in the upper diagram. So the risk is given by a color from white of undetectable up to purple that is very high. And you see there the reasons for concern, like unique and treated systems that are in danger, or extreme weather events that will increase, or the distribution of impacts that will also spread around, global aggregate impacts, as well as large scale of singular effects. And these they have shown also below with some more detailed aspects, like the warm water corals that are in danger, the mangroves, the fishing, the Arctic regions, and so on. So I don't want to bother you with all the details. You can read it by all the 3 reports of the IPCC. I would like to add just for you the temperature degrees, levels, and the probable decades when we reach it. So this 1.5 degree warming, we will reach probably till the end of this decade. And the 2 degree warming, we probably will reach around 2040. If you see this, then you see how the risk for this aspect will change just by a decade. And then you see also what kind of impact the accelerated global warming will do on it. So to come to a very short conclusion, the trend of warming is currently not reversible through reduction of CO2 emissions, but it requires a massive removal of CO2 from the atmosphere. Like I mentioned, 1/3 of the existing CO2 emission, CO2 concentration of the atmosphere has to be removed. Then the 1.5 degrees Celsius global warming until the end of the decade will probably come with the start of a massive global changes, the tipping points, and unclear interacting consequences. And next to that, it will have also an influence on the life that we are used to live by now. And as a recommendation for the future, I can only say prepare adjustments for the changes in all areas of life now, so that we still can live in a peaceful and probably also joyful life. That's my talk. Thanks for your attention.
Thank you very much, Volker. I got not only 2 questions, but also a comment via side channel. People are sitting scared and close to crying in front of their computers right now. So I hope your talk is part of lots of information we get that makes us change how we live today. For the two questions I have, we need large-scale decarbonization. Beside reducing our footprint, would it be possible to create moors or help undoing desertification to reduce the CO2 concentration in a reasonable volume?
Well, I'm not a climate scientist. All the things I have shown you, I just learned during the last year also. I have a technical and a scientific background to understand the things, but in terms of, how to say, climate activities, I'm not that expert. The only thing that I could say is, even if we are not that accurate with the measurements, even with a, let's say, with a measurement error of 10 or 20%, if you see the scales of the, let's say, the challenges that we have, then it's quite clear that we can't avoid a change. The only thing that we really can do is, by all the activities we have planned and all the things that we try to do, that we live in a better way than it could be if we don't do it. And when I got all this information, I have had the same situation like the people you mentioned next to their laptop crying. The point is, you can't change it. And it's similar. This knowledge is similar to the experience when you go to the doctor and the doctor tells you, "I'm very sorry, but I have to tell you that you have cancer or you have diabetes." But this doesn't mean that you have to die immediately, and it doesn't mean that your life will end or that you have to suffer a lot. But it means that if you want to live at least 10 or 20 years in a, let's say, also joyful and livingful life, you have to adapt. You have to take into account that you maybe have to stop smoking, maybe you have to do sports, maybe you have to change your whole lifestyle, but you have still the opportunity to live and live your life. And so it's also with us now. It's we have to accept the changes that are coming, and we can't probably avoid the huge changes because the dimensions are too huge that even an orchestrated human activity will stop it. Maybe we are able to slow the warming a bit, but we won't stop it during the next 20 years from my point of view.
And the other question, and I would just second this question, how to react to people who say, okay, we can change it anyway, so it doesn't matter.
Well, at the end, it's up to you. I mean, for what we want to convince them, of course, we have all to take activities and action. But from my point of view, they will soon change also their mind and also their point of view, because this way of living that we know and we have will change, and it will also affect their life, and probably they become scared. And my hope is that they think about their responsibility for their children and their grandchildren, and this is probably the issue, how you can get these people to at least change the behavior.
Thank you very much, Volker. It was very enlightening, and I hope lots of people have seen this and will come to the same conclusions and start acting accordingly.
Yeah. Well, I have a glimpse of hope, if you like. I have an additional slide. The glimpse of hope is like this. And when I heard this on the 1st of April, but this is not an April joke. Researcher found that 90 million years ago, close to Antarctica, there was a rainforest. And the only way this rainforest could be there was that there was a CO2 concentration of 1,100 up to 1,600 ppm. So even if it becomes worse, maybe the landscape will change, but there is still hope that somebody somehow, even not humans, can survive somehow on this planet.
Yes, probably world or this planet would be pretty much happy without humans doing whatever they please and ruin everything around us. Yes.
Yeah.
Thanks again, and a big applause